Hello, everyone. The following is the fourth in a series of lectures covering Chapter 39. Today, we will be talking about relativistic momentum and relativistic energy. So, we'll keep talking about our two observers O and O prime. One is in frame S, one in moving frame S prime. And because of the relativity of speeds depends on the frame you're on, they're not going to agree on the speed of things. And say, we have observer S just watching two particles or two pool balls, two things collide. He can measure the momentum of any particle at any given time with the trusty formula we know for momentum, which is just the object's mass times its velocity. So, what about the conservation of momentum? Well, observer S and the observer in S prime, they will not agree about the speed of the particles colliding because, again, it's relative to their own frames, but they should agree that momentum is being conserved. So whichever frame you're on, again, assuming they're all inertial frames, which we are making that assumption, despite the fact that speeds may be measured differently, if you calculate the final initial momentum, no matter your frame, you'll find that it's still conserved within the system of, in this case, these two particles colliding. So the problem is, though, that we measure momentum in the boosted frame using the classical formula here, and we're using the Lorentz velocity transformation to figure out what the momentum should be in frame S prime. We'd find that with the Lorentz transformation for the ball speed, the velocity vector for the ball u, you will not find the momentum is conserved. This is a problem because momentum should be conserved in this frame, since the postulate of relativity says that the laws of physics are the same in non-inertial frames. So both S and S prime should observe conservation of momentum, even if they don't observe the speeds to be the same. So in the same way that we had to redefine velocities, we also need to redefine momentum to make it relativity and Lorentz compatible. So we land upon the formula for relativistic momentum, which is just a classical one times a factor of gamma to account for when the object whose momentum you're measuring approaches speeds of light. And as usual with these relativistic formulas, for speeds less than, say, 10% the speed of light, usually it'll reduce to what's the classical formula you've seen before. You may also recall that if you know momentum and you have a ball, hitting the wall and bouncing back, right? There's you have some impulse happening. There's some change in momentum, and that implies that some force has acted on the object to change its velocity and therefore change its momentum. So then there's a relationship between force and momentum, which is that force is the change in momentum over time. In calculus terms, the instant change of that will be a derivative of momentum over time, which is what you see here. But overall, given that now you have a relativistic formula for momentum and a formula that relates force to momentum, then you can take the derivative of the formula here with respect to time, and you will arrive then at a relativistic force formula. And then this is essentially a Newton's second law that accounts for relativistic effects. If you look closely at the formula, I know it might be obvious, but since Newton's second law talks about how a force acting on an object imparts an acceleration, the extra gamma factor that you see in the formula actually puts a limit on how much a force can accelerate a particle. As a particle accelerates closer and closer to the speed of light, the harder it is for a force to keep accelerating it. It turns out that the acceleration, if you break down the formula here using Newton's second law and the relativistic momentum, it turns out the acceleration is proportional to this term here, which means that as the speed of the object increases, the acceleration decreases. So it gets the same force has a harder time accelerating a particle as the particle gets faster. As a matter of fact, as the particle gets so fast that it's reaching speed of light, the amount of acceleration caused by a force reaches zero. So you can never then accelerate any particle with mass to the speed of light, and this sets a hard upper limit on the speed of everything in the known universe. That is to say, nothing can travel faster than the speed of light. Not energy, not any particle with mass, nothing. You cannot send any signals. Nothing can gain information any faster than what light can travel. The implications of this is very, very, very broad, very long-standing, and very fundamental to the very notion of physics. But for all intents and purposes, just know that nothing can move faster than light. So you note then that the relativistic momentum formula, what sets it apart is a gamma factor, which we've shown that at low speeds, it's just a factor of 1. We can forget about it. But at relativistic speeds, the gamma factor tends to increase. So electrons, on their own do tend to move pretty fast. And the example here, you have an electron moving at 3/4 the speed of light. So we have to find its momentum using a relativistic formula. And if you go and calculate that, then the gamma factor for that, which is kind of shown already here, you'll see that the momentum then is about 50% as big as the classical momentum. So if you plug in the classical momentum formula, it doesn't have gamma, you see that your value is less than the relativistic momentum. And of course, right, this means that this is like true, this is a more realistic measure of its momentum. This only really works for small speeds, which is not the case here. The fact that it's bigger momentum tells you that a lot more energy is required to get it to this speed. So in the same way that we had to adjust momentum to account for the principles of relativity, we also need to redefine how we consider energy. If we stuck to the classical formulas for energy, especially kinetic energy, you'd see that when switching to a moving frame that's relativistic, you'll find that conservation of energy is not being kept. So we're going to have to comply with conservation of energy, of course. So we're going to retool our equations a little bit. So first, we're going to establish relativistic kinetic energy. And to do that, we need to consider very simple case first, which is just that we'll have some particle at rest. And, to give it energy, we need some external force acting on it. So let's say we have that. We have some force acting on the particle, doing work on it then over some distance. And with relativistic considerations, so you can calculate the work done necessary to accelerate the particle to some speed. Let's just say the speed's u. And all that work, all that energy has to go into something, right? That's going into making the particle move. So that energy is being transferred as kinetic energy for the particle. Since the particle was at rest, the initial kinetic energy was 0. So all the energy goes into its final kinetic energy. In other words, the work done is its final kinetic energy. So we already kind of have a formula here that talks about the work being done. So that's your kinetic energy formula as well. More specifically, it's your relativistic kinetic energy formula. And it might not look like it because, it's a factor of gamma minus 1, the mass of the particle c squared. But this does still reduce to the classical one for small speeds. But with the gamma factor, it ends up being a lot bigger than the classic formula, like you saw with the relativistic linear momentum. So, in fact, here they show you exactly what happens when the speed's small. Its formula comes back to the classic one. So, for something to be considered non-relativistic, again, the rule of thumb is that if you're moving at less than 10% the speed of light, the classical formula should work pretty well. But for anything bigger than 10%, you want to do the relativistic formula because it's such a true reflection of what the actual energy is. And you can actually graph the relativistic formula for kinetic energy versus the classical one as a function of the speed. So basically, you'll see that there's a cap on the speed of an object. Basically, if you're measuring the kinetic energy with the classical formula, you're following the blue curve, and you see, right, like, well, to expect then as speeds get bigger, kinetic energy increases. But we know that there's a limit, right? Nothing can move faster than the speed of light, and that's built into the relativistic kinetic energy formula, because in that one, as speeds approach the speed of light, your kinetic energy goes to infinity, which implies that an infinite amount of work needs to be done to accelerate something to the speed of light, which is impossible to do. It's worth pointing out that the curves overlap, early on for small values of the speed. Again, it's a rule of thumb that, like, if the speed's less than 10% the speed of light, you see how the classical formula, the blue line, works pretty well. So you'll note that in our relativistic kinetic energy, the term gamma, is there to account for the speed of the object, of the particle. But we kind of multiply everything in, you see that there's one term here that doesn't really count for that at all. In fact, mass is invariant, so different frames of reference, different inertial frames will disagree about the velocity of objects, even the momentum, but they will agree, in conservation of energy and conservation of momentum, and they'll also agree on the mass of the objects. So this is pretty important then, that no matter what, there's some element of energy that's proportional to the mass of the object in question. So we're going to go ahead then and define an energy component known as the rest energy that just depends on the object's mass. And the implication here then is that by just virtue of having mass, you have energy. You recall how kinetic energy is saying that by virtue of having some speed, there's some energy associated with that. Rotational kinetic energy tells you that there's energy associated with rotation. Gravitational potential energy tells you that you have energy by virtue of being in some relative height. But now we're establishing rest energy. Having mass means you have energy. Because mass is invariant, right? There's always this rest energy. So in previous physics lessons, when we were doing conservation mechanical energy or just energy in general, we never really had to consider rest energy, since the mass of things was not changing. So that was always a constant. Initial energy equals final energy. The rest energy is the same, just not really be considered at all, and since it's not changing. But it is there, and it's an important postulate. It's a very important part of relativity, since in the world of relativistic particles, particles can convert into radiation, or radiation can convert into particles. So there is exchange of mass into energy, and the rest energy formula then is able to relate that directly. Then it follows that to consider the total energy of a particle, in the simple case where there's just movement to it, then there's not just kinetic energy, but now we have to account for rest energy as well. So the total energy is just the sum of the two. And you can also calculate total energy if you know your gamma factor and you know the mass. And there's also one more way to write the total energy of a particle or anything, which is the formula here that relates the total energy to the momentum and the mass. Again, this is the relativistic formula, of course, so you want to write in gamma here when you plug in for momentum. Note that the total energy here has a square, so if you're calculating it with momentum in mind, you want to take a square root to get the total energy. So when we're talking about energies for a lot of subatomic particles, or even atomic particles, you'll find that most of their energy, especially their rest energy, if you measure it in joules, it's a pretty small value of joules. So physicists prefer to work with a more reasonable unit, which is the electron volt. And the electron volt is just it's taken from electromagnetism. So you might recall from your E&M class, if you've taken it, that electrons, are accelerated, can be accelerated through an electric field, and an electron volt basically is defined as the energy that an electron gains when it's accelerated from rest through a 1 volt potential. So it's a small measurement of energy. It's just 1.6 times 10 to the negative 19 joules, but it turns out that it's roughly the amount. It's a good measurement for energies of particles. If you want to consider the rest energy of an electron, then it's pretty small in joules. You can see that here, but it's a nice number of like about 0.5 mega electron volts. And on top of that, physicists like to leave constants just there, like the speed of light or Planck's constant, rather than plugging the speed of light every time. Since it's always going to be a constant, they just kind of tend to keep it as part of the units. You can kind of see here they're stating the mass of the electron in terms of its rest energy over c squared. They don't bother to plug it in because they know it's a constant. They're not too worried about it. As a matter of fact, a lot of physicists in the field of cosmology, astrophysics, particle physics have their own sort of system of units where it's built so that constants like the speed of light are just set to a value of 1, just to make things simpler. It's called natural units. Okay, so this quick quiz here is pretty cool because it gets you to think about how rest energy and energy are related. In this first part, you want to rank the 3 particles from greatest to least according to their mass, and you're told 2 things. You're told their rest energy and the total energy. So the rest energy is what tells you about their mass, right? It doesn't depend on speed, just the mass. It's proportional to the mass, so the first 2 just have a rest energy of E, but the last one has twice that. So this one must be the heavier particle. The other 2 are tied since they have the same rest energy. Now you have to rank them in terms of kinetic energy. So we know the rest energy and the total energy. We're assuming that everything else is kinetic energy. So if you take the total energy and subtract away their rest energy, that tells you the kinetic energy. So the difference here is just E. The difference here is 2E. The difference here is also 2E. So particle 2 and 3 should have the most kinetic energy, and particle 1 has the least. Finally, we have to rank them according to their speed. This is a bit trickier because the speed does depend on the kinetic energy. But recall that unlike classic kinetic energy, that kinetic energy is proportional to the speed squared. The speed for relativistic kinetic energy is a bit trickier to find because there's the speed tucked inside the gamma factor. So if you take the formula that we learned before just now, here, the total energy being related to momentum, if you plug in relativistic momentum here, you have a factor of gamma, which then you can solve for the speed of the particle. You can end up deriving a formula that straight up tells you that the speed of a particle is related to both the rest energy and the total energy. And overall, from a formula you get, you'll find that the bigger the ratio between the rest energy and the total energy, the smaller the speed. In other words, whichever has the smallest ratio of rest energy to total energy will have the biggest speed. So that's actually particle 2 because it's a ratio of 1 over 3 here, while the other particles have a ratio of 1 over 2, which is bigger than 1 over 3. And so the second particle is the fastest. And the rest of the examples is just finding the rest energy of a proton. And the examples really speak for themselves, but I like the last part of the example where they compare the kinetic energy. What you get using relativistic formulas is 4.7 times the rest energy, which had we used the classical ones, the kinetic energy would have only changed by a factor of 4. So again, relativistic formulas tend to give you bigger values of energy compared to the classic ones, which again is telling you that you need to put in a lot of energy to get things moving faster and faster. And oh yeah, one more thing before I forget. We know that photons, which are the particles of light, are massless. So if you're looking at the total energy for a massless particle, this term will just go away. There will be no rest energy associated with a photon. We just have a term here for the photon's momentum. And of course, the photon's momentum will be determined with a different formula than the one we've seen, because the one we've seen accounts for mass. So given that they're massless, there's another way to find the photon's momentum, which we'll talk about in the quantum mechanics chapter. But for now, that takes us to the end of the journey for special relativity. There is two more sections at the end of this chapter that introduce general relativity. These are only supplemental and will not be part of your assessments or evaluations. However, if you ever have time, it is worth reading because it is an even broader picture of how spacetime works, and it is quite interesting and certainly much more broad and unique from any other topic of physics we've seen so far. But for all intents and purposes, this does end the um, part of the chapter that you need to know for the course. So after this, we'll jump into the world of quantum mechanics. So I'll hope to see you then. Thank you.